wanted to talk a little bit about transformers today. And today we'll start off, we'll just look at some transformer schematic symbols, and we'll talk about the different parts of the symbols and just kind of get familiar with how these things might look on a schematic. So right here, if you look at the first one on the left here, we can see the designator is T1. Alright, so T1, okay, so that just stands for Transformer 1 typically. The left side is going to be the input, or what we would call the primary side, and that's the side where the voltage or the source would be applied. Okay, and on the right hand side is the secondary side. Alright, so the secondary would be like the output. Now technically these things are reversible, so you could put voltage on the secondary side, but now that becomes the primary. Alright, so some other things that we would see from the first thing you're going to want to look for or try to figure out is we have what's called the turns ratio, and this one is 1:4, so that's a 1:4 turns ratio. And so what that means, and we'll see it more, or we'll understand it more when we do an analysis, basically for every turn of winding on the primary, we have 4 turns of winding on the secondary. So basically the primary comes in and we might have 1, 2 turns. So here on the secondary we're going to have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so now those magnetic fields are going to be interacting with each other, and when we do analysis we'll talk more about how that works. Okay, so other things that you're going to want to pay attention to, so we've got the turns ratio, the designator, what the primary side, the secondary side. So you'll see down the middle of these solid bars, that indicates the core material. So these inductors, so let me just draw, basically we have a core material, maybe a piece of iron. Okay, so the primary windings come in, okay, and wrap around there, and so now that core, that iron core, when a magnetic field is developed, that magnetic field will couple, or the iron will help couple the magnetic field to the secondary. Okay, so they're mutually coupled. So we're using basically inductors that share a common core, which the net effect is we get that mutual inductance effect. So any varying voltage on the primary will induce a varying voltage on the secondary. And so these things are really cool, and we can use those to do a lot of things. And actually you'll see those, and you'll see transformers in a lot of electronic equipment throughout your career. They really are everywhere. So let's talk about these core materials. So on this first one you see the 2 solid bars. Okay, so that indicates iron core. Okay, and so that iron will help concentrate that magnetic flux and help you know, mutually couple those windings. So now the problem with that is, you know, it has we start to, as frequency increases, we start to see core losses. So we'll get eddy currents in the core, hysteresis losses, and so as frequency goes up, the power losses for an iron core are going to start to increase. So if you need a higher frequency, you go over to this next transformer. Now you notice there's a dash, the lines are dashed, so that's ferrite. Let me see if I can spell it correctly. Ferrite. And so basically that's a ceramic material that has iron powder in it. And so the idea is in an iron core, you know, eddy currents would just kind of flow around, you know, randomly. Basically current is flowing in that iron, and it's drawing power and basically just creating heat in the core, which is not doing us any good. So ferrite is ceramic with little particles of iron that are not touching each other necessarily. So therefore you might get some teeny tiny eddy currents within each little particle, but you're not going to have current just flowing around all throughout the core. And so what that does is it reduces some of that, some of those core losses, and allows you to run at a little bit higher frequencies. Now if you need to run at really high frequencies, even that might be too much loss. So you come over here and you have an air core. Basically that is just what it sounds like. You know, the windings are either around like a cardboard or a plastic tube, or they're just wound and then shaped, and so there literally is nothing but air down the center of the transformer. All right. So the next one, on the end here, basically there's a couple of things here that are unique about this last transformer that has the 1 to 100 turns ratio. So I didn't really talk about it, but there's this middle pin in this right here, and we call that the center tap. And so basically what that does is it creates a voltage divider. So we have the whole secondary here, okay, but now we have a voltage divider. So as voltage is induced from the primary into the secondary, we could measure from A pin to B pin and see the entire secondary voltage, but now that center tap literally is just in the middle of that winding. We have another lead that connects to the center, or so there's basically, now we have two secondaries. So secondary. Alright, so the net effect here, let me get rid of some of this clutter. Basically, so now I have 3 pins with which I can create an electrical contact and use for my circuit or to take measurements. So I could measure the V from AB, the V from BC, okay, and the entire secondary would be the VA to C. Alright, so when we do analysis, we'll actually look at those numbers and voltages and see what those actually look like. Alright, so the next thing, it's a very subtle change, or a very subtle difference between this symbol and the rest of them, is there's these little dots. And see, there's a dot up on top on the primary and down here on the secondary. And basically that just describes the phase relationship from the primary to the secondary. So if you have the turns wound in the same direction, clockwise or counterclockwise, basically if you have, you know, primary, you know, you're going to have a sine wave coming in, and then the secondary is going to be in phase. Okay. Alright, so for the first 3 schematics, the secondary is going to be in phase. When you have these little phase indicator dots here, alright, now the secondary is going to be 180 degrees out of phase. So basically the primary winding could be going clockwise, and the secondary winding could be going counterclockwise. So basically that mutual inductance effect is just happening. It's still happening, but if you measure the A to C pin, you could see it's 180 degrees out of phase with the primary, and so that would basically just look like this. There we go. So basically that's the only difference, is that when the windings are opposite, it flips the phase, and so it's 180 degrees out of phase. And so that's just something to keep in mind. It may be a concern, or you may not care, depending on the type of circuit that you're building. Alright, so that's a little bit about transformers, their symbols, and what the symbols mean.